Okay, to conclude our discussion of Chapter 15, I want to have you guys interconvert between solubility product and solubility. The solubility product, which is KSP, is not the same as the solubility of a given salt. So KSP, like any other equilibrium constant, is a constant. Solubility is a specific value that changes with different conditions. It's defined as the maximum amount of salt that you can dissolve in a given volume of solvent. Usually that solvent is water, sometimes it's other solvents. In this class, we're going to be talking about water, primarily as the solvent in which salts are dissolved. So they're not the same. KSP is unitless. Solubility always has units. The units can be moles per liter. It can be grams per liter. It can be grams per milliliter. It's some amount of salt that can dissolve in a given volume of solvent. So you'll have either moles or grams, some kind of mass as the numerator of the unit, and the denominator of the unit will be a unit of volume of solvent. So they're not the same. KSP and solubility are not the same, but we can calculate one from the other. And I want you guys to get very good at interconverting between them. It's pretty simple. You can use the strategies that you've used to solve equilibrium problems to interconvert between solubility product and solubility full stop. So I want to do an example of going in both directions. The first example I would like to try is to calculate the solubility of lithium carbonate. Oh, sorry, not to calculate the solubility, but I'm telling you what the solubility of lithium carbonate is. The solubility of lithium carbonate is 7.4 times 10 to the minus 2 moles per liter. Notice it has a unit. That number means that I can dissolve a maximum of 7.4 times 10 to the minus 2 moles of lithium carbonate per liter of water. Okay, it's the maximum amount of salt that can dissolve in a liter of water. So from that value, can I calculate the solubility product, KSP, of lithium carbonate? Okay, so this solubility, I'm going to call it little s. 7.4 times 10 to the minus 2 moles per liter. This is the maximum amount of lithium carbonate that can dissolve in a liter of water. So let's start by writing a dissolution reaction for lithium carbonate, Li2CO3. When I put that salt in water, I am going to get 2 lithium plus 1 ions and a carbonate anion. And of course, carbonate is a complex anion. It has a 2 minus charge on it. Something you can figure out from the stoichiometry of the salt, or you might have memorized the carbonate ion and its charge way back in Gen Chem 1. Either way, you can figure out what that is. Now, underneath that reaction, I'm going to make an ice chart. And I'm going to call the amount that I start out with the solubility, S. So I'm going to say, this is the amount of this that I have that can dissolve in water. Because that's what this is telling me. This is the maximum amount that can dissolve in water. So that means over the course of the reaction, I'm going to get minus S on the reactant side. And then on the product side, I'm going to get plus something in relation to X. I have to look at the stoichiometry, though. My ratio here, I need that balanced reaction because my ratio here is 2 to 1. So that means I'm going to need to gain 2S for the lithiums. And carbonate has a 1-to-1 ratio with lithium carbonate, so I'm just going to gain plus S there. So my equilibrium concentration for carbonate should be S, and my equilibrium concentration for lithium should be 2S. 0 plus 2S is 2S. So now let's use that reaction to write an expression for KSP. Just looking at this reaction, KSP is going to be equal to the concentration of the lithium ion squared times the concentration of the carbonate anion. And I can plug, since this is an equilibrium expression, I can plug my equilibrium values into this expression for KSP. So that is going to be 2s squared, because lithium concentration is 2s, and then I have to square it because I've got that exponent there. That's how I got that squared. And then carbonate is just plain old s. All right, so 2 squared is 4. S squared times s is s cubed. Okay, and I know what s is. I was given s in the problem. S is the solubility. So I just need to plug this value for s into this expression, and that gives me the KSP. So the KSP is going to be equal to 4 times 7.4 times 10 to the minus 2 cubed. And if you do that arithmetic, you should get a value of 1.6 times 10 to the minus 3 for your KSP for lithium carbonate. Of course, it's an equilibrium constant, so it's unitless. So that is how you calculate KSP from a solubility. Now I want to do a problem that goes in the opposite direction. I would like to calculate solubility from a KSP value. So let's do a different color for this calculation. Let's calculate the solubility of silver phosphate. The solubility of silver phosphate. So silver phosphate is Ag3PO4. And I want to do it in moles per liter of water. The KSP for silver phosphate is 1.8 times 10 to the minus 18. That's a teeny tiny number, right? So this is only very, very slightly soluble salt. Okay, so first we want to write an equation for the dissolution of the salt. So here's my silver phosphate. It's only slightly soluble. For every mole of it that dissolves, I'm going to get 3 moles of silver plus ion and 1 mole of phosphate. And of course, phosphate has a 3 minus charge on it. Okay, so I can see that reaction is balanced in both elements and in charge, because the 3 pluses balance out the 3 minus on the phosphate to give me a neutral compound. So based on that reaction, I can write a KSP value. I can also make an ice chart, just like I did in the last problem. So let's do both. Before I do my ice chart, I want to write the KSP expression based on the reaction that I wrote. So the reaction must be balanced so that I can get the proper KSP expression. I have silver cubed times phosphate. Okay, based on that balanced reaction. Okay, so once again, the solubility is the amount of the salt that can dissolve. So I want to use that amount to dictate how much I'm going to gain in the ions, in the actual dissolved ions on the right side of the equation. And once again, I just use the stoichiometric ratio. So I'm going to have 3 moles of this for every 1 mole of salt that dissolves. So that means this is going to have to be a 3s. 0 plus 3s is 3s. For phosphate, I just have 1s because of the 1-to-1 molar ratio of phosphate to silver phosphate. So 0 plus s is s. So now I can plug these equilibrium concentrations into my expression for KSP. I am going to have 3s cubed, because I take this, plug it in for silver, and then I have to cube the whole thing. I'm going to plug this s in for phosphate. So 3s cubed times s. And that is going to all be equal to, what's 3 cubed? 3 times 3 times 3 is 27 times s raised to the 4th power. And I know my value for KSP because the problem gave it to me. KSP is 1.8 times 10 to the minus 8. So I can solve for s. 27 s to the 4th equals 1.8 times 10 to the minus 18. Solving for s, let's see, I get s to the 4th power equals 1.8 times 10 to the minus 18 divided by 27. That should give you something around 6.67 times 10 to the negative 20th. And then taking the 4th root of that number, so you can raise that number to the power of 1/4. If you need to be reminded of how to do that, you can actually just type it into your calculator like this, and then raise it to the power of 1/4 or 0.25, however you prefer to input it. That is going to give you a value of, I think I need only 2 sig figs here, 1.6 times 10 to the negative 5. And just like any ice chart, it's going to be, I don't know what this is. It's just like any ice chart, it's going to be in moles per liter. Just like in all the equilibrium problems we've done so far. So this is the solubility of silver phosphate. Okay, this is the maximum number of moles of the maximum amount of silver phosphate that can dissolve in a liter of water. So I hope that showed you how you can calculate solubility from solubility product and vice versa.